This is our third lecture on statistical testing, and we continue to talk about tests for the coefficients in a linear regression model. As an example, we continue to consider the effect of cost of education on income later in life. But this time around, we make the model a little bit more involved. We still have income on the left-hand side, but then on the right-hand side we have two variables. We have the cost of high school education, let's call it cost HS, and we have the cost of college education, cost capital C. And then we have an error term. To make this example relevant for countries where education is at least partially state-funded, assume that, for example, the cost of high school includes all costs, so maybe costs directly to the consumer of education, like tuition fees, but also taxpayers' money that is funneled into education. And the same for the cost of college. Previously, we were interested in testing the null hypothesis that the cost of education has no effect on income. In order to test this economic hypothesis, we have to translate it into a hypothesis about the coefficients of our linear regression model. Previously, that was pretty straightforward because we had only one single coefficient associated with cost of education. So what we did, we just set that coefficient to 0. But now we have two coefficients that represent effects of the cost of education. If we are saying cost of education never matters, it means it doesn't matter in high school and it doesn't matter in college. Therefore, our null hypothesis translates to the hypothesis that we have both beta 1 equal to 0 and beta 2 equal to 0. This means in order to test this economic hypothesis, we now have to test two simultaneous restrictions on coefficients. Testing multiple restrictions is called a joint test. One way you may be inclined to go about testing this hypothesis is to look at its two components and say, look, I know how to test these hypotheses. I can test each of those using a two-sided t-test. So why don't we just start by doing two-sided t-tests? We set the nominal level of each test to alpha. And then we can see how we can combine the results of the two t-tests into a conclusion about the validity of our hypothesis. Let's call the first component of our joint hypothesis H01. And let's call the second component H02. We can think of our joint hypothesis as saying that the restriction in the first component is true, that means H01 is true, and simultaneously H02 is true. Our test of H01 can reject or not reject. Similarly, our test of H02 can reject or not reject. This gives us a matrix of 4 possible outcomes. Let's indicate rejection of our joint hypothesis with a big red X. We shouldn't believe in our joint null hypothesis if we lose faith in one of its components. This implies that we should reject the joint hypothesis if at least one of the two t-tests rejects. This gives the decision rule to reject if both tests reject, or if one rejects and the other doesn't. The only scenario where we wouldn't reject is if both t-tests fail to reject. What is the size of our combined test? In other words, what is the probability that we reject our joint hypothesis if the joint hypothesis is true? it can be shown that this number can be any number between alpha and 2 times alpha. Where you end up between these two numbers depends on the correlation structure of these two tests. If they are always in agreement, so if they either both reject or both don't reject, then the size will be alpha. If they're always in disagreement, so that if one test rejects, the other doesn't, so we're always here, then we end up at the 2 alpha. For anything between the two extremes, we get intermediate numbers between alpha and 2 alpha. If I choose my alpha to be 10%, this here says that the size of the combined test may be as bad as 20%. If I want to be sure that my size is no more than 10%, of course what I can do is to choose alpha equal to 5%. This is called Bonferroni corrected multiple testing, and is a completely legitimate way of constructing a test of our joint hypothesis. However, it has one very severe disadvantage. To explain what this disadvantage is, suppose that the size here works out to be 8%. By choosing alpha equal 5%, we've made sure that the size is no more than 10%. 8% is less than 10%, so our size guarantee holds, which is great. What is not so great that between these two numbers, we are wasting 2%. What do I mean by that? Well, by choosing a test with a size of 10%, we were saying we are happy to accept a probability of type 1 error of 10%, but instead we got 8%, a lower number. That means our test is a little too conservative. It is a little too careful not to reject too often. It could reject more often and still meet our requirement of a size of 10%. Why is that a problem? Well, if it were to reject more often, it would be more powerful. And what we want are powerful tests that meet our size requirements. We don't want tests that are undersized and therefore less powerful than they could be. An efficient way to test our joint hypothesis is to use an F-test. The F-test is also known as a Wald test. To explain what an F-test is, we have to specify its null hypothesis, its test statistic, and its decision rule. We'll see shortly that we can use the F-test to test a rich set of different null hypotheses. For now, we focus on our example hypothesis. The null hypothesis is that beta 1 is equal to 0, and beta 2 is also equal to 0. We denote the test statistic of the F-test by capital F. Like the t-statistic, the F-statistic is a measure of divergence that measures the difference between the estimated betas and the betas that we hypothesized. Unlike the t-statistic, F takes on only positive values. A large value of F indicates that we are estimating betas that are very different from what we hypothesized, and a small value of F indicates that we are estimating betas that are very similar to what we hypothesized. A good way to think about F is to think of it as a measure of the estimated distance from the null. This intuition is more than enough for this course. We will not be discussing a formula for F. We now move on to the decision rule. The F-test will reject if the estimated distance from the null is too large. In other words, we reject if F is larger than some critical value C alpha. We can apply the same reasoning as for the t-test. In general, we like small c alphas because they mean that the test will reject often and will therefore be a powerful test. On the other hand, we don't want C alpha to be too small so that we reject too often, in the sense that we don't control the probability of type 1 error. That is, C alpha should be such that the size of the test is guaranteed to be alpha. To determine an appropriate value for C alpha, we have to consider the behavior of the test statistic if the null hypothesis is true. If the null hypothesis is true, then F has approximately an F distribution with df1 and df2 degrees of freedom. This approximation holds in large samples. There are many different kinds of F distribution. df1 and df2 are shape parameters that tell us exactly what kind of F distribution is the relevant one. df1 is also called the numerator degrees of freedom, and df2 is called the denominator degrees of freedom. The numerator degrees of freedom is the number of tested restrictions. In this example, we are testing 2 restrictions, so this number is 2. The denominator degrees of freedom is the number of observations in our sample minus the number of betas in our model. In our example, we have 1, 2, 3 betas, 1 intercept and 2 slopes. So the number of betas is 3 and our denominator degrees of freedom is n minus 3. Let's take a look at how the F distribution behaves for different degrees of freedom. Let's fix the denominator degrees of freedom. Let's assume that we have 150 observations, so that we have 147 denominator degrees of freedom. If the denominator degrees of freedom is a reasonably large number, then the behavior of the S distribution will not be very sensitive to what the exact number is. In econometric applications, the denominator degrees of freedom is usually very large because we tend to have large sample sizes. So denominator degrees of freedom doesn't matter that much. The numerator degrees of freedom, on the other hand, matter a lot. This animation shows how the shape of the F distribution changes as we change the numerator degrees of freedom. The denominator degrees of freedom are kept fixed at this number. We choose C alpha equal to the 1 minus alpha quantile of the F distribution with df1 and df2 degrees of freedom, where df1 and df2 are defined here. Different parameters will give us different critical values and therefore different decision rules, as illustrated in this animation. For this animation, I've set alpha equal to 5%. This means the shaded region has area 5%, and is therefore the same area for all plots. Maybe it doesn't look like it. This is because for small numerator degrees of freedom, the right-hand side tail of the F distribution is very thick. This means that there is probability mass in the far right-hand side that we can't see in this graph. The main thing that I want you to take away from this animation is that the critical value crucially depends on the degrees of freedom. Now we have completely defined the F-test. Let me show how to conduct an F-test using Stata. We will use our example model and example hypothesis. Here I am in Stata. I've already loaded my completely fake data set. I can run our regression income on cost high school and cost college. I will ask for robust standard errors because that's the right thing to do. Get some regression output. Now I want to test whether beta 1 is equal to 0 and at the same time beta 2 is equal to 0. This will not work because Stata doesn't know what beta 1 and beta 2 are. So beta 1 is my coefficient on cost of high school. So instead of beta 1, I'll just write cost of high school, and Stata translates this to mean the coefficient on cost of high school. And similarly for beta 2, I'll just write cost C, so the slope coefficient on cost of college. First, Stata reminds us of the null hypothesis that we're testing. It computes the value of the F statistic, of the test statistic. We don't know how to compute this value, but Stata knows. Then Stata reminds us of the relevant reference distribution for computing the critical value. It's an F distribution with 2 numerator degrees of freedom and 147 denominator degrees of freedom. Now, Stata doesn't compute the critical value, so we're not really able to determine whether the test rejects or not. Well, we are using this output, but we're not quite there yet. For now, let's compute the critical value by hand. We want a quantile of the F distribution with 2 and 147 degrees of freedom. Let's say we want the 95% quantile. So that corresponds to an alpha of 5%. And we want to print this. Okay. So now here's our critical value. It's a little over 3. The realized test statistic is way bigger than 3. And this means the test rejects. What do we conclude if the test rejects? If we reject our null hypothesis, then we believe it to be false. What does it mean for this null hypothesis to be false? It means that out of all the possible configurations of beta 1 and beta 2, we're ruling out one configuration, and this is the configuration where they are both equal to 0. This means, by proving that the null hypothesis is false, we have shown that at least one of the betas is non-zero. For example, one way for the null hypothesis to be false is if beta 1 is equal to 0, but beta 2 is unequal 0. This corresponds to the case where cost of high school doesn't matter, but cost of college does. This here is just an example hypothesis. We can use the F-test to test many other kinds of null hypotheses. For example, if we had 3 regressors, we could easily test 3 slope coefficients simultaneously. For example, beta 3 equals 0 could be added to this joint hypothesis. Now we would have 3 restrictions instead of 2, so we would have to change the numerator degrees of freedom from 2 to 3, and that's basically the only thing that changes. Staying within this example where we only have 2 regressors, maybe we don't want to test them against 0. Maybe it is meaningful in our application to test them against other numbers, for example, 3 and 4. Again, we have 2 restrictions, so the numerator degrees of freedom is unchanged at 2. Let's carry out this test in Stata. Instead of testing against 0, we test against 3 for this coefficient and 4 for this coefficient. Stata computes a test statistic of 2.43, which is below the critical value. Therefore, this test does not reject. This means we cannot rule out that beta 1 has the value 3 and beta 2 has the value 4. We can use the F-test to test even more kinds of null hypotheses. In general, we can test all hypotheses that can be written as multiple linear restrictions. What is a linear restriction? Suppose that we have k-slope coefficients, so we have beta 1, beta 2, beta 3, up to beta k. A linear restriction can be written like this. Here the a in front of the betas are numbers specified by the researcher, and the b1 here is also a number specified by the researcher. We can have multiple such linear restrictions. Let's say we have q of them. For this general case, the number of restrictions would be q, and the denominator degrees of freedom would be n minus the number of betas in the model, and this would be 1 intercept plus k slope coefficients. Therefore, the denominator degrees of freedom would be n minus k plus 1. This may look quite complicated, but in most practical applications it's not. This is because for most of the null hypotheses that you're likely to test, a lot of the a's will tend to be 0. We continue to consider our old example of the effect of cost of education on income. Suppose that we want to test the null hypothesis that money spent on high school education is equally effective as money spent on a college education. In terms of our model coefficients, this means we want to test the null hypothesis that beta 1 is equal to beta 2. We can rearrange this equality as beta 1 minus beta 2 equal to 0. This is a linear restriction. Why is that? We can think of the beta 1 as being pre-multiplied by an a11 that is equal to 1. So this would be our a11. This minus may as well be a plus, but then to keep the expression unchanged, we have to pre-multiply the beta 2 by a minus 1, and this would be our a12. Then the 0 here obviously is our b1. If our regression model had more than the 2 regressors that we have here, then we would just add plus 0 times beta 3 plus 0 times beta 4 and so on as long as needed. This shows that this here is a linear restriction. To determine the critical value for testing this hypothesis, we have to figure out the numerator degrees of freedom. That's the number of restrictions, and there's only one restriction here. Let's implement the test in Stata. We want to test the hypothesis that the coefficient on cost high school minus the coefficient on cost college is equal to 0. Again, Stata repeats the null hypothesis to us, computes the critical value. Now we have only one numerator degrees of freedom. This means we cannot use the critical value that we computed above here. We have to change the numerator degrees of freedom to 1. The denominator degrees of freedom stays the same. The relevant critical value is computed to be a little below 4. The realized value of our test statistic is 0.21, very small, much smaller than the critical value. This means we don't reject. Us not rejecting means that we have not been able to prove that the income effect of spending money on high school is different from the income effect of spending money on college. Now we've conducted several f-tests in Stata, but we still don't understand all of the output. I'm talking about this line here. This number gives the p-value of the test. The p-value allows us to determine whether the test rejects without having to compute the critical value. Let me explain what exactly the p-value is. As an example, let's consider the null hypothesis that both beta 1 and beta 2 are equal to 0. Under the null hypothesis, the f statistic has an f distribution. This means this is the relevant distribution for looking up the critical value. For this example, we've already discussed which f distribution is the relevant one. We know that the reference distribution is an f distribution with 2 numerator degrees of freedom This is a plot of the density of this f distribution. Before we move on and talk about p-values, allow me to rant a little. Please don't say that this here represents the distribution of the F statistic. A lot of people say that. What is true is that this distribution approximates the distribution of the F statistic if the null hypothesis is true. But if you think a little bit about how statistical testing works, you as a researcher probably don't believe that the null hypothesis is true. So to you, this is an unlikely shape of the distribution of the F statistic. So please don't say that the reference distribution is equal to the distribution of the F statistic, or at least don't say so without further qualification. That's it, that's the end of my rant. Let me explain what p-values are. P-values are tightly linked to critical values. Here the critical value is the unique value C alpha, such that if I integrate under this curve, starting at C alpha and moving into the right hand side tail, then I obtain this area, and this area should be equal to alpha. Or equivalently, if I integrate under this curve up to C alpha, then I obtain an area of 1 minus alpha. That's really just saying the same thing. I can use this critical value to determine whether the test rejects. I observe the test statistic F. And now if F is below C alpha, I don't reject. If F is above C alpha, then I will reject. Let's suppose F is here, but that I don't know the numerical value of C alpha, so I cannot compare F to C alpha. I can still figure out whether the test rejects. What I can do is that I can integrate under this curve starting at F. This means I'm computing this area. This area is called the p-value. Since f is a function of the sample and therefore random, so is the p-value. Here in this example, we observe f smaller than the critical value. What does this imply for the p-value? Note that integrating from C alpha to infinity gives us area alpha. But to compute the p-value, we started integrating earlier, so we obtained this additional area. Therefore, the p-value has to be larger than alpha. These two statements are equivalent. Clearly, if the F statistic is smaller than the critical value, we don't reject. This means if the p-value is larger than alpha, we don't reject. By reversing the order of F and C alpha, we can show similarly that observing F larger than C alpha, which corresponds to a rejection, is equivalent to observing a p-value smaller than alpha. Therefore, observing a p-value smaller than alpha means that we reject. A good way to think about p-values is as a way of measuring the size of f against the benchmark distribution. We know that we reject for large values of the test statistic, but what is a large value? That may not be immediately obvious to us in F space, but it is obvious to us in p-value space. In p-value space, an F statistic is large if the p-value is smaller than alpha. This animation shows how different values of the F statistic map into different p-values. The horizontal dashed line represents a nominal level of 5%. Based on the p-value transformation, we can determine easily what values of the F statistic exceed the critical value at level 5%. We don't even have to compute this critical value. The last thing left for us to do is to look at p-values in Stata. We'll start with this test, where we tested two coefficients against 0. We obtained a test statistic of a little over 12, much bigger than the critical value, so we reject it. Alternatively, we could have determined rejection by looking at the p-value, which is very close to 0, so definitely smaller than our nominal level of 5%. Then we've also looked at this test, where we tested the hypothesis that one coefficient is 3 and the other coefficient is 4. We obtained a much smaller test statistic of 2.4, smaller than the critical value, so we didn't reject. We arrive at the same decision by looking at the p-value. The p-value is just below 10%, definitely larger than our nominal level of 5%, so here also the p-value says we don't reject. This concludes our discussion of the F-test.